Hello everyone, and welcome to my presentation about virtual threads in action. This talk was actually scheduled for my friend from Athene, but unfortunately because of the health issues he couldn't come, so I should greet you all by his name, and by Dmitry Alexandrov, that's his name. And instead of him, I will be delivering this talk. All right, so my name is David Král, and I am a Helidon developer at Oracle. There is an email address and Twitter account you can reach me out if you'll have any question about the Helidon or the virtual threads and you would like to discuss those. And now let's take a look into the beginning, because even if we will be talking about the virtual threads, we should start from the beginning, which is the Project Loom. So let's take a look into what Project Loom is. The Project Loom is a project to explore and incubate Java VM features and APIs for implementation of the virtual threads. That's essentially what Project Loom is. It consists out of 3 JAPs so far. The first one is virtual threads, which is actually scheduled to be Java 21 GA, and it's under JAP 444. Then there is structured concurrency, which is scheduled to be a preview feature in Java 21, and it's under JAP 453. And lastly, there are scoped values, also scheduled to be preview features in Java 21. The most importantly for us right now will be the virtual threads, since those virtual threads are actually the most important, the most interesting stuff, because they will be generally available without the need of other flag to enable those. So I'll talk briefly about all of these 3, but I'll start with the virtual threads right now. So let's take a look into the virtual threads itself. If you never heard about the virtual threads, you might ask, all right, what is virtual thread and how does it differ from the, let's say, original or regular thread we have been using until this point? The virtual thread is a thread which you can have a huge numbers of. And if I'm saying huge numbers, I mean like really millions of those. And without the threat of wasting your resource, wasting your system out of the memory. So the virtual threads are using the thread API, and that means you will not even know that you are in virtual threads, since it's the same interface. Virtual threads are this echo. The virtual threads are scheduled by the fork join pool, and you use it this way, because every task you will submit to this fork join pool, or this specialized fork join pool, will be run as a virtual thread. One thing important to note is that all of the virtual threads are always daemons, so you can't set any priority to those. Also, all threads will have a group virtual threads, and they do not have any permission with a security manager. Okay, so what happened to the original thread? Well, it's still there, but right now it's called platform thread. So if we are talking about the virtual threads, the platform threads, we will be referring to those as well. And right now, those are backed by the kernel threads one by one. Those are actually those which were causing the memory problems and why we couldn't just block everywhere and do not care about the memory. Now let's take a look into how virtual threads works, because virtual threads themselves are using platform threads underneath, because otherwise they wouldn't be able to work. But the virtual thread mounts the platform thread, or the carrier one, as it's also called, to be able to run, and as soon as it detects any blocking operation, it will unmount, and it will free this platform thread to be able to run some different virtual thread, different operation, and stuff like that. So if we'll take a look into this example I'm having below, as you can see, the first two lines, the first one line is generating some random number, and then we are executing some call to some other service. And we are getting some completable future here, and on the next line, we are actually using a blocking operation, the get one. At this point, the virtual thread, which was executing the request, is blocked, and essentially what that means, that it unmounts the platform thread, it does nothing at this point, and the platform thread will be able to perform other operations until this virtual thread is unblocked. Once this completable future is completed by the thread which is handling the request, it will be then, let's call it, revived, and it will be remounted to the platform thread to continue running as normal. Right, so virtual threads are also bringing some new APIs. I was mentioning already the fork join pool for scheduling the tasks to run as a virtual threads, and that's actually something we can do because of the method new virtual thread per task executor. This is a new method which returns us this specialized executor to be able to schedule these tasks. There is also a method called isVirtual added to the thread to be able to know whether the thread is virtual or it's not. With this knowledge, with virtual threads, we can now write applications which are written the blocking way, but without actually caring about the blocking points. And that's great, because it's basically like reactive programming, but without the hassle or without the danger of getting ourselves into the callback hell, which is, I think, those among you who used reactive programming, I think you know what I'm talking about here. And also, writing code blocking way is more, let's say, natural and easier to read, easier to write even, and easier to maintain, because it's much simpler. And with every feature, that's something common for everything basically, there are certain limitations. So it is important to know the limitations of each technology or feature you will be using to be able to avoid those pitfalls you might fall into. Now, we will take a look into the first two limitations of virtual thread. For example, if you'll try to use some operating system level operations such as reading the file or writing the file and stuff like that, this will not unmount the virtual thread from the platform one. And the reason for that is it's on the native level, and Java doesn't know that it should be done. So there is no way for us to know. Another thing is the JDK limitation itself. So if we'll call wait method out of the object class, it will also not unmount the thread. By the way, in terms of those OS level limitations, there is one interesting part that, as far as I know, JDK team is actually working on some improvements at this area because, for example, in Linux, there are specialized APIs for bringing some, let's say, asynchronous file system operations, and Java team is trying to find a way how to optimize that. But so far, this is not there, so keep in mind that this will not work. I mean, unmounting will not work. But fortunately for us, these two operations are detected or detectable by the JVM, and it will compensate for us. So even if this happens, and that means if we will block the platform thread underneath the virtual thread because unmounting didn't happen, Java will compensate for us and temporarily increase the number of threads in our for join pool. So we will not stop running or anything. It will be covered. Then there are, let's say, more severe limitations, which might actually hinder your application scalability, as the scheduler does not compensate by extending the parallelism, as in the previous case. The first one is the usage of the synchronized blocks. Don't get me wrong, synchronized blocks are quite okay to use, but at the moment you will actually block inside of the synchronized block, it will cause an issues with the virtual thread and the platform thread that it will not unmount again. And that's not good, right? Also, native methods and foreign methods, it's basically, or foreign function, it's basically the same. But in these two cases, since we will not receive any compensation in terms of threads or in terms of increasing our scheduled executor, the for join pool, this can actually really cost us some performance. Okay, so how to deal with that? How to deal it the way that we can have the same functionality as the block code, for example, provides, and use the virtual thread as well? Well, we can use reentrant lock, or basically any other lock which is present in Java util concurrent, because these locks are optimized for virtual threads. And locks can offer basically the same functionality you would like to have with the synchronized blocks itself. So if you would like to use virtual threads and you are having synchronized blocks with the blocking operation inside of it, just rewrite it with the usage of the locks and you will be all right. Now let's take a look into the structured concurrency and what it is. The structured concurrency brings us a better support in terms of the handling the subtasks we would like to execute. And what I mean by that is that, for example, right now, if we would have some executor servers, we would schedule some task there to run, and we would receive some future, and you will say, okay, so just block until this is done. Let's imagine we have spawned like five subtasks this way. And we care about finishing all of them, not like one of them or two of them and stuff like that. Right now, we would basically have to wait the whole time it will run. And what if the fifth one, for example, failed? Like after a few milliseconds after the start because it couldn't reach some endpoint, for example. Well, right now, we would have to complete all of the tasks previously scheduled, and then we would get to the point which failed, and we would fail there. But this is not exactly optimal because, to be fair, we are wasting resources. So structured concurrency solves exactly that. we will spawn 5 subtasks. We will we will execute those, and once any of them fails, the structured concurrency kills the remaining which are running, and it will report back the exception which occurred. So this simplifies the stuff quite a lot, and we are not wasting the resources at all at this point. Also, some interesting thing to note is that there will be support for it in thread dumps. So if you need to investigate the dump for some failure and stuff, you will even see those scheduled tasks there present. You will see how many of them and stuff like that. If you are interested in playing with it, just take a look at the structured task scope class, which contains pretty rich Java doc, which will guide you through how to use it. Or there are also some articles on the internet which might help you as well. Then there are scoped values. Scoped values are meant to be as a replacement for thread locals. And the reason for that is that the thread locals are having several disadvantages or design flaws, let's say. But, well, let's take a look at those. Because I'm having those listed here as well. These are the reasons why to not use thread local, or at least think about using the the scoped values. For example, one of the disadvantages is mutability. Right now, the thread locals, or the content of it, can be changed from basically any place in your application which has access to this thread local instance. You can change the value which was assigned there, and that's definitely not good. Because, for example, if there is some security context and you can rewrite it from any place of your application, it's kind of security an issue. So be really mindful where you are using the thread locals in general, and once this scoped value stuff is released, consider updating into this. Because they are bringing some even more advantages here, I mean the scoped values. For example, lifetime. In comparison to the thread locals, the value will be assigned to the scoped values just for a time. It really needs to be there. And by that I mean, in thread locals, we have assigned a value to the thread local, and it remained there until we removed it. And, well, we did not every single time, so it was there even longer than it had to be. With the scoped values, it will be there for known period of time because it's bound to some method execution, but you'll see it if you'll test with it or play with it a bit. And in terms of inheritance, it's kind of expensive to copy the values to the child threads with the thread locals, and scope values solves this as well. And now let's take a look into how we in Helidon we played with the virtual threads, because we were thinking, since we are running on the Netty, and Netty is very performant server, we are thinking about, okay, virtual threads sounds promising. It brings blocking way of coding, and it basically feels like reactive programming as well. But without the need to deal with it ourselves, it is done for us basically by the JVM. So we were thinking what to do with that, and whether it would be even possible to have performance of the reactive server with the easiness of coding blocking code. So we have done some tests there, and that's Helidon Nima was born. But before continue in terms of the Helidon Nima, we will take a look at the brief introduction of Helidon. So Helidon is a framework for Java, for developing Java microservices. All of you, everything you develop at Helidon is basically just a regular Java SE application. You are having a jar file, which you can easily execute, just simply by java -jar and the name of the jar. And the advantage of it is you can easily test your application on your local host, for example, without the need of specialized server to be present. And also, it simplifies the containerization of the application and stuff like that. Now, let's take a look into very brief history, because Helidon 1 was released at 2019, and we were targeting Java 8 there. Since then, we have moved the base version of the Helidon quite a lot to bring our users the newest features of Java as soon as possible. And in 2020, we have released Helidon 2, which is based currently at JDK 11. And the second live and developed version of Helidon is Helidon 3, which is based on JDK 17. And this year, around the release of the JDK 21, we would like to release also Helidon 4. And that's the reason why virtual threads are so important to us, because we would like to introduce there the Nima as well, as a part of it. Now, let's take a look into some trade-offs we had to deal with when we were developing the applications before Helidon Nima. And I do not mean only in terms of the Helidon, this is in general. Basically, we had two ways to develop our application. We could either use the easiness of code or the easiness of use, or we could target to performance. Well, if we wanted to follow the easiness of use, we would be using blocking paradigm, we would be having quite a lot of libraries to choose from, we will have very easy maintenance, troubleshooting, and basically everything like that. But the performance might suffer, and there we might have problems, for example, because of the number of threads. Because the threads we were using are, or were, the scarce resource. And scheduling too many tasks which would be blocking could lead to thread starvation. And that's something we are trying to prevent, obviously. And that's the reason for reactive paradigm. Reactive has a great performance. It offers really very high speed and everything, but to be fair, it has a steep learning curve. Troubleshooting and maintenance, well, it's not exactly optimal. And I think that vast majority of you who encountered reactive programming will agree with me. When you saw it the first time, it was not like the first hit, it was like, yeah, this is the way I want my code to look like and I want to program. But it was basically something you had to choose if you wanted to fully utilize your threads and waste no resources and make your code as performant as possible. In Helidon, we are having two flavors, Helidon MP, which is following the blocking paradigm, and Helidon SE, which is offering the reactive one. And the Helidon SE is actually running on top of the Netty, so it's pretty fast. Now, let's get back to the Nima. Helidon Nima was basically the result that we didn't want to do these trade-offs. We wanted to merge it together. And Helidon Nima is exactly that. Because Helidon Nima allows us to, or was built from the ground up and designed for virtual threads. There is no leftover code. There is nothing we didn't rewrite to support threads because it's completely brand new. And I'm proud to say that we have managed to do it the way that we are having a performance of the reactive programming with the simplicity of blocking code. The core of the Nima itself is the web server. And the Nima, as you might see it here, is just a code name of the project. It doesn't mean that this is a new flavor of Helidon. It doesn't mean that this is a new repository or the new product in general. Actually, it's not. It will be integrated into the Helidon directly. Now let's take a look into how Nima is actually handling the virtual thread. Because for HTTP 1 requests, we are having one virtual thread. It will be responsible for reading request data from connection, invoking your route, and writing the stuff you want to send back. Of course, it can be tweaked, it can be improved. If you enable asynchronous write options, it will spawn another virtual thread for it. But to be fair, the best utilization of the virtual threads are actually coming with the HTTP 2. Because we are spawning one virtual thread per connection and also one virtual thread per stream. And also important to know that all of your routes are executed as are executed with a virtual thread, so you can block as much as you want. Right, now let's take a look into some graph here about the performance. This is about Helidon MP and comparison between running on Helidon SE as the reactive server, which we used until this point, and Helidon MP running on the Helidon Nima. So I don't know how it's visible. Okay, so it is. So the darker column is the previous or the older approach with the Helidon SE, the reactive one. As you can see, with the Helidon Nima, we were able to double the performance of what we used to have with just a simple request containing some JSON. And with usage of the HTTP2 with TLS enabled, we were even able to quadruple this performance just because using virtual threads. And that's great. So how we have managed to do so? Well, we were avoiding context switching as much as possible. That's one of the things. And also because we were using the blocking code with the virtual threads, which is handling all this offloading or unmounting of the thread for us. So you might ask also, how about the other Loom features? Will these features be included into Helidon as well? Well, yes, eventually. Once they are generally available, we will definitely be including those. But right now, as of release of 4.0 version, we will not, because these features are not generally available, and you would have to enable those by the specialized flag. So we are not doing this in the release. We will obviously be playing with it around, but not in release. And now let's take a look into some lessons we have learned during the developing of the Helidon Nima. Because we had to unlearn the asynchronous programming. I know it sounds weird, but when we were developing it, we were so used to use asynchronous programming. It actually felt strange for us to not trying to do the stuff non-blocking and actually getting back to the times when we could block everything. But with the blocking, and when we finally realized that we really do not need to do asynchronous stuff, it made everything easier to write, easier to read, and especially easier to maintain, which is one of the most important stuff. With virtual threads, there might be some issues, so you need to check with the vendor of your library you would like to use with the virtual thread, whether there will be any impact when using it. Because in most of the cases, I think there will not, because it's just a thread. But there might be if the library is blocking in some way. So yeah, check with the vendor whether they are virtual threads compliant, rather than assuming they are. Also, we had to remove all of the synchronized blocks out of the code we had, because, as mentioned before, synchronized blocks and blocking operations were not fitting well together. So, as long as you are not using blocking operations inside of the synchronized blocks, you can freely use it. There is no reason for not to. And I've mentioned it during the scoped values, but simply think about the places where you are using thread locals, and consider updating the thread locals to scoped values once this feature is released. And I think that, or we think in Helidon, that the virtual threads are one of the best features actually added to Java ever, because they solve so many stuff. It changes everything in terms of how the microservices are developed and what problems we will be solving. One thing we were kinda, let's say, surprised when developing it, not that the simplicity brings performance, this is kinda obvious, but we wanted to use actually a non-blocking socket, and we discovered this non-blocking socket was actually slower than the old plain simple socket which we are usually not using. And the reason for it is because we can block. We do not need to deal with the non-blocking code, and it was much simpler. And if it was running on the virtual thread, it was just fine. And also, it made SSL much easier. So that's one of the reasons why it's much faster. Also, interesting stuff was we intended to reuse buffers, not to create a new buffer for handling a new requests and stuff. But actually, we found out that this is detrimental to our performance. It was actually better if we created a new buffer every single time. And yes, we also were thinking, okay, but what about the memory, right? Because if you are having millions of running threads and you are creating for all of these threads new buffers, will not your memory suffer? Actually, it will not. I mean, obviously, yes, it will increase its consumption a little bit, but nothing devastating for applications, and JVM is fast enough to clear these buffers pretty quickly. So it's actually something we have discovered and kind of didn't expect. One thing important to note, if you will be using virtual threads, do not expect that the technology will be configured the fastest way possible by default. Always play with some configuration options. For example, we have several of them like TCP no delay, asynchronous sockets writes, and basically try to fine-tune the socket configuration for the best outcome. But it really depends very heavily on the operating system you are using and the JVM implementation you are using. So always try to test that, because fine-tuning this will lead to even better performance than you would expect. And the last slide in terms of the lessons we have learned is actually that the HTTP2 is not easy. When we are developing it, we have encountered that this is sometimes hard to understand what's going on the line. But to be fair, HTTP2 provides the best utilization of the virtual threads and also showed us that we can create the millions of threads. We are having this measured actually, and really it was there. I was surprised when I saw it. Also, we have managed to create gRPC support based on the HTTP2, and because of that, now we will be able to run the gRPC endpoints on the same port as HTTP1, HTTP2, and, well, now the gRPC. It can be all on the same port. Because of that, we are now capable of fully removing netty dependencies, and we will be replacing that with a Nima implementation. This is one question we are quite often getting. What if there will be an obstruction of a thread? What if I will have some long-running task performed inside of the virtual thread on some endpoint, for example, which will then be using your platform thread out of that pool you are using to schedule everything else? Well, create a new executor for it. That's the best way you can do. Because this is something you can even solve with the reactive programming. You would be basically having the same problem there. That's something you shouldn't do. So if you want to solve this long-running problem, basically just create a new executor service, execute there this long-running task, and then in that virtual thread where you are executing it, just place .get method. It will block the virtual thread which you do not want to be wasted with the long-running task, and it will solve your problem. You will be able to then continue with running this code after this long-running piece of code is ready. And that's basically something very similar to as in terms of reactive, where you would place it under the then except. Now, might be interesting to compare how blocking code is actually simplifying the overall code you need to write in your endpoint. So on the left, we are having here code written for our Helidon SE. As you can see, it's following some reactive paradigm. It uses our reactive operators here. And actually what happens here is that we are having some client executing GET request to some endpoint. It's not important where. And then it's requesting the response entity to be handled as a JSON object. Only these two lines are actually executed in the server thread. Because once this has been performed, the server thread is then returned to the pool to be reused by some other request. And the rest of it, those map operations here, or the error handling, or for single here, is actually done by the thread of the client. Because we are not blocking, we are not waiting for the client to complete the call, and that's how the reactive works, right? Which is fine, but it can be confusing when you see it the first time, and it's not as exactly intuitive. Because, to be fair, if I was the one who sees this for the first time, I would assume that the maps are executed in the same thread, and then I would be very surprised when my debugger wouldn't stop there, and instead of that, it would be skipped. So that's one thing. And now let's compare it into the blocking. As you can see, the client performs exactly the same request, but instead of scheduling some mapping operations to it, we will just say, all right, once this is done, by the way, because this is a different client, this one is blocking one, not a reactive one as this one. But the API is the same, or nearly. And right now, we are performing the request, we are waiting for it to finish, and once it's done, we are getting the string status out of the JSON object we have obtained, and that's the same as Reactive did, right? And then we are just sending this status back to the original requester of this endpoint. So you can see how much simpler the overall code is, and how much easier it is actually to read. And if you compare it with the performance of the reactive code, this is simply the way, which way to go. And this is basically it in terms of my presentation. These are some links where you can find resources about the Helidon. Feel free to reach out if you will have any questions about the Helidon, about Nima, or you will need help with something related to that, obviously. So, especially on Slack, we are quite often monitoring it, and we are trying to provide as accurate responses there as possible. And that's basically in terms of my presentation. Thank you. And yeah. And also, if you have any questions, either ask them right now or stop me on the hallway, for example, and ask those. That's fine. Yeah. Yep.
There is some notification when virtual thread is unmounted or remounted?
No, there's not. It's happening underneath. Java will handle it for you. And if you are running like millions of threads, and each of it will print out some notification for you that it has been unmounted, it would be just a lot of code. Sorry, a lot of text. All right. If there are no further questions, I have probably one last thing. I have a stickers here if anyone wants. So that's it. Thank you very much. Bye-bye.